Parallel resistors can be added together by adding the reciprocal of their values and taking the reciprocal of the result. For example, the following three resistors can be combined into one resistor by adding their reciprocal values and then taking the reciprocal of the final result. Note that I converted them all to have the same common denominator 18, added the numerators, and found that the result was 11 over 18. Then I flipped that to be 18 over 11 ohms. So this circuit can be written with the equivalent resistor 18 over 11 ohms. Now let's talk about what this equivalent circuit actually retains from the original circuit. Obviously, it doesn't retain the current passing through the 3 ohm, 6 ohm, or 9 ohm resistors, but it does retain the current passing through the battery, which is the current that splits up into the 3, 6, and 9 ohm resistors. In general, any set of parallel resistors that are directly parallel, mind you, can be combined by adding together all of their reciprocals. Let me just add 1 over Rn here, and setting that answer equal to the reciprocal of the equivalent resistor. So when you add them all together, you get the reciprocal value of the resistor that you'd like to have that could replace all of those parallel resistors. This equivalent resistor captures all the current that goes into and then splits off into all of the resistors that you combined and preserves the current that exits all of the resistors that you combined. It also preserves the voltage drop across all of the resistors. Note that every single one of these resistors has the same voltage drop because they're all in parallel with the battery. So if you just replace them all with one resistor, they'd have one voltage drop. Let's talk about the justification for this equation. Consider the following circuit. We know that this battery creates a 12-volt voltage rise. So any particle that passes through the battery gains 12 volts of energy. It's worth noting that batteries can push out basically unlimited amounts of current. The way that a battery works chemically is just trying to establish a specific voltage drop between its two terminals, and so it will do anything it must to create that voltage drop, including any extent of current that it can create, up to physical limits, which are usually described by the physical battery you have. So let's consider that each of these resistors has the 12-volt voltage drop, because they're in parallel with the battery, and any particle that exits the battery has to use up all 12 of its volts to return. Across this resistor, there's a 12-volt drop, so I'm just going to erase that and say that 12 volts, remember that I is equal to V over R. So the current across this 3 ohm resistor is 4 amps, and the current across this 4 ohm resistor is 3 amps, and the current across this 6 ohm resistor is 2 amps, again because you take the voltage drop and divide it by the radius in order to get the current. We can see that because of Kirchhoff's current law, the amount of current entering this stretch of wire needs to be 4 plus 3 plus 2, which is 9 amps of current. So when there are 3 resistors in parallel, the battery is outputting 9 amps of current. But if there was only one resistor, it would only output a total of 4 amps of current. This makes sense because 12 divided by 3 is 4. So what we're seeing is that the addition of more resistors in parallel actually causes the battery to draw more current. Remember that the battery is trying to drive particles through the circuit. If it can drive particles in 3 different ways, then basically it will be able to drive 3 times as many particles, assuming they all have the same amount of resistance. The battery will use up its energy faster this way, that is true, but that doesn't matter to the battery. What matters to the battery is driving the particles through at a 12-volt potential. So if you have more resistors experiencing the same voltage drop of 12 volts, they will all drive the battery to draw more current for every single parallel resistor. In total, we observe that 9 amps of current are traveling through the circuit, and there's a 12-volt voltage drop, so we can determine an equivalent resistor where R is equal to V over I is equal to 12 over 9. That is a 4 over 3 ohm resistor. Notice that 4 over 3 ohms is less than 3 ohms, 4 ohms, or 6 ohms. The addition of more resistors makes the circuit act like it has less resistance total, and less resistance implies that more current is traveling through the circuit. One way to think about this less resistance is that even though there are more resistors, there's more paths for the battery to shove particles down. And the effect of having many paths to go down kind of overwhelms the effect of each resistor. Let's say we had a group of parallel resistors which all were experiencing a certain voltage drop V. And let's say they were experiencing some current traveling into the group of 3 resistors I. The voltage is the same across each resistor, but each resistor has its own current, which we will call I1, I2, and I3. Of course, all their 3 currents add together to the total current entering and exiting the circuit. That means I is equal to I1 plus I2 plus I3. Let's say we wanted to replace these 3 resistors with one equivalent resistor. Then this I could be imagined as the total voltage V divided by the total equivalent resistance R. This would be one resistor that would produce I current given V voltage. And then of course, I1, I2, and I3 can all be written as V over R1, V over R2, and V over R3. This is because, remember, V over R is equal to I according to Ohm's law. And you can see that all the V's cancel out, so you're left with the equation 1 over R equivalent equals 1 over R1 plus 1 over R2 plus 1 over R3. And then to get the equivalent resistance, you just have to take the reciprocal of whatever answer you got from adding all of these together. This is a current source. It acts like a battery, except that it drives the circuit to be at a certain current. So only 1 amp can travel through this current source, but 1 amp will always travel through this current source. Given the following 2 resistors, we are asked to determine the current I2, or let's call it I6, in this 6 ohm resistor. If we only knew the voltage drop across this 6 ohm resistor, we would be able to determine what the current is because we could take the voltage and divide it by the resistance. But we don't have the voltage drop anywhere here. So to analyze this circuit, we will combine the 2 resistors using the equation we were given below. 1 over R equivalent equals 1 over 2 plus 1 over 6. 1 over R equivalent is equal to 3 over 2, so the total resistance in the circuit combined is just 1.5 ohms. Note that's the reciprocal of 2/3. 3 over 2 is 1.5. Now, this circuit, we can easily determine the voltage drop of this resistor. The voltage drop of this resistor is the current times the ohmage. So, V equals IR equals 1.5 volts. The voltage drop across this resistor is 1.5 volts. However, this doesn't tell us the voltage drop across the 6 ohm resistor, except that it does. We can decompose this 1.5 ohm resistor into the original 2 resistors that created it, and then say that the voltage drop across either of those resistors is 1.5 volts. Then we can divide 1.5 volts by 6 ohms to get that I6 equals 0.25 amps. Just like the voltage divider in the last video, we can describe something called a current divider, which, given a current that's passing through a series of parallel resistors, will tell you the current traveling through any one of those resistors. To do so, I will describe to you the concept of conductance. Conductance, or G, is 1 over R. That means that if I equals V over R, I equals VG. So let's say you have a total current I, and then you have 3 mini currents I1, I2, and I3. These are equal to VG1 plus VG2 plus VG3. The ratio of I1 to the total current is the ratio of I1 to all of these currents combined. And we can rewrite I1 as VG1, and then cancel out all of the V's to get that, and then multiply the I up here to get that I1 is equal to the total current times the ratio of the conductance of the resistor through which I1 is passing divided by the total conductance of all 3 resistors. Let's rewrite this circuit in terms of conductance. We have 8 amps of current, and we have 0.5. The unit is either S for Siemens. Siemens is Siemens. or upside down omega. I'm going to use upside down omega. The three resistors on the left here have the conductance described by these three values. So if I want to determine the current through this 2 ohm resistor, it is going to be 8 amps, the total current, times the conductance of this 2 ohm resistor, which is 0.5 Siemens, over the total conductance, 1 Siemens. 1.25 Siemens. That gives us 3.2 amps of current traveling through this 2 ohm resistor. By a similar argument, 3.2 amps go through this 2 ohm resistor, and 1.6 amps go through this 4 ohm resistor, which makes sense. Doubly powerful resistor should probably have half as much current going through it, and these three numbers add to 8 amps, so our equation is working. To use this equation, you do not actually need to rewrite this circuit in terms of Siemens. You can just take the reciprocal of all of these resistors and add them together to get this total conductance. And then you can put the conductance of the one resistor you want on top of the total conductance. Anyway, that's the current divider. Note that R1, R2, and R3 are not in parallel. The combination of R1 and R2 is in parallel with R3. You can only combine resistors together into an equivalent resistor if they're directly parallel with each other. That is, they start and end in the same place. In this area, all three resistors start and end on the same stretch of wire, so they can be added together as if they were in parallel. These resistors cannot until you combine R1 and R2, because the branch of R1 and R2 is parallel with the branch of R3. Thankfully, R1 and R2 can be added together very easily.